Assalamu alaikum, brothers and sisters. Welcome to the journey of Quest, where we quench your thirst of knowledge. Have you ever wondered why some rocks can exist in different forms under the same conditions? Well, the answer to this puzzling question is deeply rooted in the principles of thermodynamics and is explained by a fundamental concept known as the phase rule. The phase rule, you see, is not just a mathematical formula, but a pivotal principle that helps us understand the complex world of petrology. So what exactly is the phase rule? Simply put, it's a principle that allows us to foresee the number of degrees of freedom or variables that can be independently changed in a system at equilibrium. It's a bit like being able to predict the outcome of a game of chess by knowing the number of possible moves. Now you might be wondering, how does this rule fit into the realm of petrology? Well, in the world of rocks and minerals, the phase rule is somewhat of a guiding light. It allows petrologists to predict the stability of minerals in rocks under different pressure and temperature conditions. Imagine, for example, you have a rock that can exist in two different forms or phases under the same conditions. The phase rule would allow us to predict which form the rock will take, depending on the conditions it's subjected to. This is a crucial aspect of petrology, as it helps in understanding the formation and transformation of rocks, which, in turn, provides insights into Earth's geological history. The mathematical formula of the phase rule, which we'll delve into more in the next scene, might seem daunting at first glance, but don't worry. Once you understand the concept behind it, it becomes less of a mathematical monster and more of a helpful tool. In essence, the phase rule is a principle that brings order to the chaotic world of rocks and minerals. It's a map that helps petrologists navigate the complex terrain of geological formations and transformations. As it turns out, the phase rule is the key to unlocking this mystery. Before we delve into the math behind the phase rule, let's take a moment to understand its significance in the grand scheme of thermodynamics. The phase rule, as we've mentioned, is a fundamental principle in thermodynamics. But what does it mean in this context? In thermodynamics, a phase refers to a state of matter that's homogeneous in physical and chemical composition. A phase can be a solid, liquid, or gas. Now, the phase rule in thermodynamics is a principle that dictates the number of degrees of freedom in a system at equilibrium. This rule, established by Willard Gibbs, is a remarkable tool that helps us predict the behavior of a system under different conditions. The variables in the phase rule, the degrees of freedom, F, the number of components, C, and the number of phases, P, are interconnected. Changes in one can influence the others. For instance, adding a new component or phase can reduce the degrees of freedom, limiting the ways the system can change without altering the number of phases. On the other hand, increasing the degrees of freedom can enhance the system's flexibility to adapt to changes in conditions without disturbing the equilibrium. This intricate balance between the variables is what makes the phase rule a vital principle in thermodynamics. Its ability to predict the behavior of a system under different conditions is instrumental in fields ranging from petrology to chemical engineering. So, in a nutshell, the phase rule is a guiding principle in thermodynamics that helps us navigate the complex world of phases and components. Its significance can't be overstated, and as we'll see in the next scene, the math behind it isn't as daunting as it might seem. So, how does this phase rule work in practice, you might ask? Let's dive in, shall we? At the heart of the phase rule is a straightforward mathematical formula. It reads F equals sine C P plus 2. Now that may sound like a secret code, but it's really quite simple. Here, F stands for the degrees of freedom, C is the number of components, and P is the number of phases. The degrees of freedom represented by F are essentially the variables that can change without altering the number of phases. Think of it as the number of different directions you could go in a maze without hitting a wall. The more degrees of freedom, the more options you have. Next we have C, the number of components. In our maze analogy, these would be the different paths you could take. In petrology, components refer to the chemically independent constituents of a system. For instance, in a system comprising quartz and water, we have two components. Last but not least, we have the P, which stands for the number of phases. In the context of our maze, this would be the number of separate areas or sections. In petrology, a phase is a homogeneous, physically distinct, and mechanically separable portion of the system. For example, in a system containing ice and water, we have two phases. Let's illustrate this with an everyday example. Imagine you're making a cup of tea. The components would be the tea leaves, water, and perhaps some sugar. Each of these can exist in different phases: the solid tea leaves, the liquid water, and the dissolved sugar. The degrees of freedom could include the temperature or the amount of sugar. The beauty of the phase rule is that it allows us to predict the behavior of a system under different conditions. By knowing the number of components and phases, we can calculate the degrees of freedom, giving us a glimpse into the possible outcomes. In essence, the phase rule is a simple equation with profound implications. Now, let's talk about degrees of freedom. As we've learned, the degrees of freedom, represented by F in our formula, are essentially the variables that can change without altering the number of phases. They're kind of like the wildcards in a game of poker. They can significantly impact the game, yet their value isn't fixed. In the context of the phase rule, the degrees of freedom could include variables like temperature, pressure, or concentration. For instance, in our tea-making scenario, the temperature at which you brew the tea or the amount of sugar you add can change without affecting the number of phases. These are your degrees of freedom. But why are they so important? Well, the degrees of freedom provide us with the flexibility to alter the conditions of our system without changing its overall state. They give us a glimpse of the possible outcomes. By knowing the number of components and phases, we can calculate the degrees of freedom, thereby predicting the behavior of our system under different conditions. So, in essence, degrees of freedom play a crucial role in the phase rule. They are like the invisible threads that weave together the components and phases, providing us with a comprehensive picture of our system. With an understanding of degrees of freedom, we can manipulate conditions to our advantage, predict outcomes, and solve the complex puzzle that is the phase rule. So, as you can see, degrees of freedom are not just an abstract concept. They're the vital components that breathe life into the phase rule, making it a practical and powerful tool in the world of thermodynamics and petrology. But why is this rule so important in petrology, you may ask? Well, let's delve into that. The phase rule is not just a mathematical principle. It's a tool that petrologists, those who study rocks and the conditions in which they form, use to understand our planet's crust. Without it, the secrets held within these seemingly simple stones would remain hidden, veiled by the complexity of nature's processes. Imagine being able to determine the stability of a mineral or rock type under various conditions. That's precisely what the phase rule enables petrologists to do. It's like having a secret decoder ring for the Earth's crust. By applying this rule, they can predict how changes in pressure and temperature might affect the formation of different minerals and rocks. But it's more than just understanding the stability of these substances. The phase rule also helps petrologists comprehend the creation of various types of rocks. It's a bit like being a detective, piecing together a complex puzzle. Each rock type, be it igneous, metamorphic, or sedimentary, has a story to tell about the Earth's past. The phase rule helps us read these stories. Consider an igneous rock, formed from cooling and solidification of magma or lava. The phase rule can help determine the conditions under which this formation occurred. Or take a metamorphic rock formed under intense heat and pressure. The phase rule can provide insights into the environmental conditions that led to its creation, and it doesn't stop there. The phase rule also has implications for understanding the Earth's future. By understanding how rocks form and change under different conditions, petrologists can make predictions about geological events like volcanic eruptions and earthquakes. So you see, the phase rule is not just about numbers and equations. It's about understanding the Earth, its past, present, and future. It's about decoding the stories hidden within every rock and mineral. Thus, the phase rule is a petrologist's best friend when it comes to understanding the Earth's crust. Next up, components and phases. We've talked a lot about the phase rule, but what are the components and phases that make it work? Components are essentially the building blocks, the chemically independent constituents of a system. They could be elements, ions, or compounds. For instance, in a rock, the components could be minerals like quartz, feldspar, or mica. On the other hand, phases are physically distinct, homogeneous parts of the system. They're defined by their composition and physical state. In simpler terms, you could think of phases as the different forms in which a component can exist. For instance, water is a component that could exist in 3 phases: solid, ice, liquid, water, and gas, steam. Now, how do these components and phases affect the phase rule? Well, the phase rule is a formula that calculates the number of degrees of freedom in a system given the number of components and phases. The degrees of freedom refer to the variables like pressure or temperature that can be changed without altering the number of phases. The phase rule states that F equals sine C, P plus 2, where F is the degrees of freedom, C is the number of components, and P is the number of phases. Understanding the components and phases allows us to apply this formula effectively and predict how a system will behave under different conditions. So, why are components and phases so crucial in the phase rule? They form the very basis of this principle. Without identifying the components and phases, we wouldn't be able to apply the phase rule and make those valuable predictions about a system's behavior. They are the keys that unlock the power of the phase rule, allowing us to understand and predict the complex processes of nature. So, components and phases are key elements in the phase rule. They are like the yin and yang of this principle, balancing each other out and ensuring the successful application of the rule. The phase rule, however, is not confined to the lab or the field. It's a concept that transcends the boundaries of petrology, finding its way into a myriad of other scientific disciplines. Let's venture beyond the laboratory and delve into some of these broader implications and applications. First up is material science, a field that heavily relies on the phase rule. The properties of any given material are influenced by its phases, and understanding these phases is pivotal in predicting how the material will behave under different conditions. This knowledge enables material scientists to craft materials with specific properties, tailoring them to their needs. Next, we have environmental science, where the phase rule plays an equally significant role. It allows scientists to predict the behavior of various elements in different environments. For instance, it helps in understanding how pollutants behave when released into the atmosphere or how minerals dissolve in water bodies. These predictions serve as a foundation for environmental policies and management strategies. And last but not least, the phase rule has been instrumental in space exploration. It aids scientists in understanding the composition and behavior of extraterrestrial rocks and minerals. This knowledge, in turn, helps them predict what kind of environments might exist on other planets or moons. It's an essential tool in the search for life beyond Earth. But it doesn't stop there. The phase rule has implications in a variety of other fields, from chemical engineering to geothermal energy production, and even in the food and beverage industry. It's a testament to the versatility and profound impact of this rule. In essence, the phase rule is a universal scientific principle, a key that unlocks our understanding of the world around us. It helps us predict and manipulate the behavior of materials, understand our environment better, and explore the mysteries of the cosmos. Indeed, the phase rule is a powerful tool that reaches far beyond the realm of petrology. Finally, let's see how the phase rule applies to our everyday life. You may not realize it, but we encounter instances of the phase rule every day. Let's consider making a cup of tea. The water boils at a particular temperature, the tea leaves infuse their flavor into the hot water, and sugar dissolves at a certain rate. These are all phase transitions, governed by the phase rule. The different components are interacting with each other, changing their states and influencing the final outcome, which in this case is your delicious cup of tea. And it's not just tea. The food we cook, the air conditioning systems that keep us cool, the frost forming on our windows in winter, the very air we breathe, all involve phase transitions that the phase rule helps us understand. Even the soap we use to wash our hands, it cleans by creating an emulsion, a phase transition that allows oil and water to mix. So the phase rule is not just a scientific concept, it's a part of our everyday lives. It's the silent principle that governs the world around us. And understanding it, even just a little bit, helps us appreciate the beauty and complexity of our daily lives. So, the next time you brew a cup of tea or wash your hands, take a moment to appreciate the phase rule at work. It's not just about rocks and labs. It's about the world around us, the world we live in every day. So, what can we take away from our exploration of the phase rule? In the grand tapestry of science, the phase rule weaves a thread of understanding, cutting across disciplines and applications. It's more than just an equation, It's a lens through which we can view the world around us. We've seen how it helps petrologists decipher the stories of rocks, unraveling the mysteries of their formation and transformation. Remember, every stone beneath our feet carries a tale of pressure, temperature, and time, and the phase rule is our Rosetta Stone in interpreting these tales. And it's not only about rocks. The phase rule finds utility in our everyday lives too. Think about the materials we use, the foods we cook, and the air we breathe. The phase rule is there, quietly shaping and explaining our world. In the world of science, the phase rule is a shining example of how a simple principle can have far-reaching impacts. Thanks for watching us share our videos. Subscribe our YouTube channel and press the bell icon and stay curious for new uploads.